Hi everyone, welcome to Unit 21 of online course on probability distribution. So far, we have discussed distribution functions of discrete random variable, namely discrete uniform distribution, binomial distribution, Poisson distribution. And now we are going to discuss a new distribution, geometric distribution, a distribution of a discrete random variable. How we are defining geometric distribution? When we discussed binomial distribution, we considered a Bernoulli sequence of independent trials with the probability of success P. And on the basis of the binomial distribution, we are actually calculating probability, or we are finding probability of getting X successes out of N trials. And in the case of geometric distribution, what we are doing here is, you just consider the situation, a Bernoulli sequence. So, we have Bernoulli sequence, and so that means we have the sequence of trials. So, either success, suppose 1, 2, 3 trials of the Bernoulli sequence. So, it may be success or failure, etc. And the probability of success is given to you as P. So, consider a sequence, Bernoulli sequence, and probability of getting success is P. And here we are doing the random experiment, or we are performing the sequence, Bernoulli sequence, until a success is obtained. Suppose the independent trials are repeated until we have a success. So, that means in the case of binomial distribution, we are performing the Bernoulli sequence n times, and we are identifying number of successes obtained out of n trials. But here in the situation, we are performing the trials until a success is obtained. That means the sample space of that experiment. So, we are performing the trials. Suppose the first one is a success. Okay, that is we perform the Bernoulli sequence until a success is obtained. So, even that is getting a success, it may be one of the events. Or if the first trial is not a success, that is, if it is a failure, you continue the random experiment, and suppose the second trial resulted in success. So, that is E2, we stop the experiment. And if the first trial is not a success and second trial is also not a success, you continue the Bernoulli trials, and suppose third trial resulted in a success, then we stop the experiment. So, we are performing the Bernoulli sequence of trials until a success is obtained. So, that means our events are like this. It may be success or failure success or failure success, etc. And suppose you consider EK, the kth trial is our success. So, all the previous trials resulted in failure. So, if this is the situation, what is the probability of getting this one? So, P is our probability of success. And if this is the situation, what is the probability? It is QP, because the trials are independent and the probability of getting success is P and probability of getting failure is Q. And if this is the situation, what is the Q, Q into P. And if this is a situation, what is the value? Q, 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 etc. up to P, and how many Qs? K minus 1 Qs. So, we are performing the Bernoulli sequence of independent trials with the probability of success P until a success is obtained. Then the events are like this, and corresponding probability values are P, QP, Q square P, etc. So, what we are doing here, you count the number of failures preceding the first success. So, earlier we have it, if the success, if it is a success or FS, FFS. So, these are the outcomes or these are the events we have, and you count the number of failures preceding the first success. So, if this is the situation, our number of failure is 0, and if this is the event we have, our number of failure preceding the first success is 1. And if this is the situation, if this is the event we have, our number of failures preceding the first success is 2, 3, etc. So, that is, suppose you define a random variable x, number of failures preceding the first success. So, we are defining x as the number of failures preceding the first success, and you can note the values of the random variable are 0, 1, 2, 3, etc. So, let us define the random variable x as number of failures preceding the first success if we are performing a Bernoulli sequence of trials until a success is obtained. Then corresponding to this, what are the probabilities? See, if x is equal to 0, what is the probability? Probability of x is equal to 0 means what? Number of failures preceding the first success is 0. So, that means our event is S. So, that means P. Okay. So, this is our probability. And if probability of x is equal to 1, we consider what actually probability of x is equal to 1, the meaning of that one, that is probability of getting one failure preceding the first success. So, the outcome is what? Probability of Fs, and the trials are independent. So, the value is equal to Qp. So, this is our Qp. And what is next one? Probability of x is equal to 2. What is the meaning? Probability of getting 2 failures preceding the first success. So, that is probability of getting 2 failures preceding the first success. So, this is the event, and so since the trials are independent, this is Q into Q into P, or that is Q square into P. So, this is our value. So, let us see, if we are defining a random variable x as number of failures preceding the first success when we are performing a Bernoulli sequence with the probability of success P, our values of the random variables are 0, 1, 2, 3, etc. and corresponding probability values are P, QP, Q square P, etc. And then this random variable x is called a random variable follows. X is a geometric random variable with the parameter P, and x is said to follows geometric distribution with the parameter P. So, this is our random variable x that has a geometric distribution is often referred to as a discrete waiting time random variable because it represents how long one has to wait for a success in terms of failures. Suppose we are defining x is the number of failures preceding the first success. Actually, the meaning of x is how far we have to wait in terms of discrete time, how far we have to wait in order to get a success. So, sometimes this geometric distribution is often referred to as discrete waiting time random variable or waiting time distribution. And one example, let us say consider one example. Suppose of a population of consumers, 60% are reputed to prefer a particular brand A of toothpaste. Suppose if a group of randomly selected consumers is interviewed, what is the probability that exactly 5 people have to be interviewed to encounter the first consumer who prefers brand A? So, this is a practical situation where we are modeling the case, modeling this type of experiment to geometric probability distribution. What we are doing, what is the concept behind this? You have a population of consumers of which 60% are preferred toothpaste A, brand A. And so, P is probability of preferring the toothpaste brand A is 60%, that is 0.60, and not, that is probability of failure, that is 0.40 suppose. And as a market survey, a group of persons are randomly selected and interviewed. And what is the, suppose the first person, second person, third person, fourth person, fifth person. On the basis of that interview, if a group of randomly selected consumers is interviewed, what is the probability that exactly 5 people have to be interviewed to encounter the first consumer who prefers brand A? So, this is the person preferring the brand A. So, fifth person. So, that means fourth person interviewed not preferring the brand A. Third one not preferring brand A. And second person not preferring brand A. And first not preferring brand A. So, that is we are interviewing persons whether you prefer brand A or not preferring. So, success and failure, 2 outcomes, and first person this is a failure. So, the probability is Q, and this is also a failure, probability is Q, this is failure Q, this is Q, and this is P. So, that means suppose we have x is equal to number of failures preceding the first success. How many failures here? 4. Suppose you count the x as the number of failures preceding the first success. So, x is equal to 4. This is equal to q power 4 into p, because q into q 4 times and p, and that is 0.40 power 4 into 0.60. So, this is the probability of that particular event. That is, suppose in a consumer's market survey, suppose persons are interviewed and asking the question whether you prefer brand A or not, and 60% consumers of that population are preferring brand A. By the previous experience we know that. So, in an interview we encounter the first consumer who preferring brand A with probability this 0.40 power 4 into 0.60. So, this is a geometric distribution model. Similarly, another example you consider, suppose probability of hitting a target in any attempt is 0.3. What is the probability that it would be hit on the second attempt, or it would be hit on the third attempt, or like that? That is, we are hitting a target, and that is, suppose hitting the target. So, that means hitting the target, that means there are two possibilities, either hit the target or not hit the target. So, success and failure, and hitting the target in any attempt is 0.3. So, probability of hitting the target is 0.3 you are given, and of course, the probability of not hitting the target is 0.7. So, it is a Bernoulli sequence with the probability of success 0.3, and we are performing the experiment until we hit the target. So, the first trial, second trial, third trial, fourth trial, etc. And the question here is, what would be the probability that the target is hit on the second attempt? That is, this is hit by the second, it is not hit, or this is failure. Actually, this is failure and this is our success. So, that is Q and this is P. So, what is the probability of hit the target in the second attempt means only one failure preceding the first success, that is Q into P, or that is 0.7 into 0.3. Suppose we are making this into the 10th attempt, suppose the problem is probability of x is equal to 9, that is preceding the first attempt, first success, there are 9 failures. So, that is 0.7 power 9 into 0.3. So, the situations like this, where we can apply the geometric distribution to find the probability values. So, here we introduce the geometric random variable. So, geometric random variable, actually the definition of the geometric random variable is this one: a random variable x is said to follow geometric distribution with a parameter if its probability mass function is given by f of x is equal to q power x into p, where x is equal to 0, 1, 2, 3, etc., and p plus q is equal to 1. So, if this is the probability mass function, we write the x as geometric with the parameter p. And also you note that this is our f of x q power x into p. So, the meaning is actually probability of getting x failures preceding the first success. So, probability of x failures preceding the first success is our q power x into p. And note that this summation of f of x, sum of f of x over x, x have the values from 0 to infinity, and this is equal to sum of x is equal to 0 to infinity q power x into p, and that is simplifying, you will get this value is equal to p into 1 plus q square plus etc., or that is p into 1 minus q all power minus 1, or that is p divided by 1 minus q. 1 minus q is p, and that is equal to 1. So, that satisfying the condition that it is a probability mass function. So, summation over x, f of x is equal to 1. So, this is the definition of the geometric random variable with the parameter p, and usually p is considered as the probability of getting success and q is the probability of getting failure, and we are performing the random experiment of Bernoulli sequence of trials until a success is obtained, and count the number of failures preceding the first success. And we actually considering the geometric random variable and the binomial random variable, both cases are based on the binomial Bernoulli sequence of trials. What is the basic difference between the binomial random variable and geometric random variable? binomial random, in the case of binomial random variable, we are fixing the number of trials. That is, we are performing the trials and Bernoulli trials n times. So, that is, so 1, 2, 3, etc. up to n trials we are performing, and you count x is the number of successes. And probability of x is equal to x you are finding. This is the situation in the case of binomial random variable. We are performing n trials, and out of n trials you count the number of successes obtained, and also you find the probability of getting x successes out of n trials with the probability of success p, and that is our binomial random variable probability mass function. But what is the difference between geometric random variable? Here we are performing the experiment not by fixing the number of trials, but we are performing the random Bernoulli trials until a success is obtained. That is, n is not fixed here. So, geometric random variable is actually performing the Bernoulli sequence as many as times until the first success is obtained. So, here n is fixed, binomial random variable n is fixed, but in the geometric random variable we are not fixing the number of trials. That is the basic difference between the binomial and geometric. Rather than that, binomial random variable or binomial probability mass function gives the probability of getting x successes out of n trials, whereas geometric random variable gives the probability mass function of geometric random variable gives the probability of getting x failures preceding the first success. And now we are establishing some important properties of geometric random variable. First of all, we are finding what is the mean of the random variable. If x is a geometric random variable with a probability mass function f of x is equal to q power x into p, where x is equal to 0, 1, 2, 3, etc., and p plus q is equal to 1, then what is the mean of the distribution? And mean is given by this expression, expectation of x is equal to q divided by p. So, for a geometric random variable, mean is equal to ratio between probability of failure and probability of success. So, q divided by p. How we establish this? So, we have by formula expectation of x is equal to, see, expectation x, we know it is sigma over x, x into fx, and where fx, for a geometric random variable, fx is equal to q power x into p. So, substitute, it is sigma over x is equal to 0 to infinity x into q power x into p, and that is equal to p into q plus 2q square. By substituting different values of x, you will have those values, and this is actually p into q is taken outside 1 plus 2q plus 3q square plus etc. And this is a non-series, non-infinite series, and the value we know it is 1 minus q all power minus 2, or that is p q divided by 1 minus q the whole square, or that is q divided by 1 minus q is p, so p square, so 1 p is cancelled, so we have q, because we have the 1 minus q is equal to p. So, for a geometric random variable, we can derive the mean of the random variable as q divided by p. Similarly, we are finding the variance of the random variable, and how to find the variance of the random variable. And to get the variance of the random variable, first of all we find expectation of x into x minus 1. And to find the variance, we find the factorial moment, first factorial moment, that is x sigma over, this is expectation of x into x minus 1, that is equal to x into x minus 1 into fx, and that is and see, this is sigma x is equal to 0 to infinity x into x minus 1 cube power x into p. When you substitute x is equal to 0, this becomes 0, x is equal to 1, this becomes 0. So, the only thing is that this infinite series start from x is equal to 2 to infinity x into x minus 1 cube power x into p. And just make this expression as you take the 1, see p is taken outside. So, okay, p, and instead of from cube power x you take q square outside and 2 also is taken. So, 2 is cancelled by adding here. So, x into x minus 1 divided by 2 q power x minus 2, that way we can write. So, when we consider expectation of x into x minus 1, we can write this expression like this, and that is modified into the form of 2 p q square sigma x is equal to 2 to infinity x into x minus 1 divided by 2 q power x minus 2. What is the advantage of writing like this? Because this series is a non-series, non-infinite series, because you know sigma over x is equal to 2 to infinity x into x minus 1 divided by 2 q power x minus 2, this is equal to actually you have it is 1 minus q or power minus 3. This is a standard infinite series. So, 1 minus q or power minus 3 is obtained. So, this is equal to 1 minus q is p. So, p power minus 3, that p power minus 3. So, this becomes 2 q square divided by p square. So, when we are finding expectation of x into x minus 1 using the standard result, this result we can have the value of expectation of x into x minus 1 as 2 q square divided by p square. Now, we are in a position to find the variance. The variance is actually, our variance of x is equal to expectation of x square minus expectation of x the whole square, and expectation of x square x into x minus 1 we have as earlier we have the established with that expectation of this q is this one. So, 2 q square divided by p square, and so expectation of x square is equal to expectation of x into x minus 1 plus expectation of x. Okay. So, that is 2 q square divided by p square plus earlier we established expectation of x as q by p. So, this is expectation of, using the expectation of x into x minus 1, we have expectation of x square, this one. So, you consider the variance of x now. Variance of x is equal to expectation of x square, that is 2 q square divided by p square plus q divided by p minus q divided by p the whole square. Expectation of x the whole square means q divided by p square. And simplifying, you will get, so this is 2 q square plus p q minus q square divided by p square. So, that is equal to 2 q square minus q square. So, q square plus p q divided by p square, or q is taken outside, q plus p divided by p square, and q plus p is equal to 1. So, q divided by p square. So, this is our value. So, for a geometry random variable, we establish expectation of x already as q divided by p, and then the factorial moment we calculated expectation of x into x minus 1 as 2 q square divided by p square. From that expression we can calculate expectation of x square by this simplification, and substitute the values in the variance formula, we have expectation of x square minus expectation of x the whole square is equal to q divided by p square. So, just note, for a geometry random variable, the mean is equal to q divided by p and variance is equal to q divided by p square. So, from this, what is the conclusion? The conclusion is, for a geometry distribution, variance we have q divided by p square and mean is our q divided by p. So, variance is q divided by p square, variance is q divided by p square and mean is q divided by p. So, suppose we are considering variance divided by mean, q divided by p square divided by q divided by p, that is equal to 1 by p, that is greater than 1. And so, that is variance of x is greater than mean of x, expectation of x. So, this is a very important characterization of this geometry distribution, variance is greater than its mean. In the case of binomial distribution, in the initial stage we discussed the binomial distribution and its mean and variance, where mean is larger than variance. In the case of Poisson distribution, we obtain the mean and variance, and mean and variance are equal in the case of Poisson distribution. But this is a model where variance is greater than the mean. So, whenever we have a situation in which variance is greater than its mean and similar to the binomial distribution or Poisson distribution model, and if the situation is variance is greater than its mean, then we can model that situation, that model that experiment using the geometric distribution. So, this is an important characterization of the geometric distribution, variance is greater than its mean. Okay. And what about the mode of the distribution? So, when you draw the graph, see the q power x into p is the probability mass function, f of x is equal to q power x into p. So, these are the values. So, when x is equal to 0, it is p. When x is equal to the first value, it is p. When x is equal to 1, it is qp, that is smaller than this one. When x is equal to 2, it is q square p. And these values are the successive terms of the geometric series. That is why this distribution is known as geometric distribution also. And maximum value of the probability mass function is corresponding to x is equal to 0, that is p, that is 1. So, for a geometric distribution, mod is at x is equal to 0. And another characterization of the geometric distribution we can establish here. If x and y are two independent geometry random variable with the same parameter p, we can find the conditional distribution of x given x plus y, and that is a uniform, discrete uniform random variable or discrete uniform distribution. That is, if you are given x and y as two independent geometric random variables with the same parameter, of course, the conditional distribution of x given x plus y is a uniform distribution. Let us prove that result. Probability of x is equal to k given x plus y is equal to n. We are finding this conditional distribution. What is given to you? You are given that f of x is, or probability of x is equal to x is equal to q power x into p. And similarly, f of y or probability of y is equal to y is also geometric with the q power y into y, sorry p, because both have the same parameter. And so, if it is, how do you establish this conditional distribution is a uniform distribution, discrete uniform. See, let us just change this value x is equal to k intersection x plus y is equal to n divided by probability of x plus y is equal to n using the conditional probability definition. Or we can rewrite this value as already x is taken the value k. So, of course, the random variable y have the value n minus k. X plus y is equal to n. So, x is already assigned the value k. So, the only possibility for y is n minus k divided by probability of x plus y is equal to n. So, that is equal to probability of x is equal to k into probability of y is equal to n minus k divided by probability of x plus y is equal to n. So, when we are considering the situation that x and y are geometry independent geometry random variable having the same parameter p, probability of x is equal to k given x plus y is equal to n is equal to this value. Now, the problem is we have to find what is probability of x plus y is equal to n. So, how to find this probability of x plus y is equal to n? Suppose we are finding this probability of x plus y is equal to n, that means we can write this is equal to some probability of x is equal to r and y is equal to n minus r and all the possible values of r is equal to 0 to n. Okay. So, the probability of x plus y is equal to n can be written as sigma r is equal to 0 to n, probability of x is equal to r, y is equal to n minus r, because this x plus y is equal to n is possible if you write x as x is equal to r and y is equal to n minus r, and r, the possible values of r are any value from 0, 1, 2, 3 etc. up to n, maximum value is n. Why the maximum value n? Because it is a geometric random variable, so it can have only positive values, and this is equal to sigma x is equal to 0 to n. Since x and y are independent, this is written like this. Okay. And this is equal to sigma over x is equal to 0 to n. This is q power r into p. This is q power n minus r into p. And this is equal to p square is taken and sigma x is equal to 0 to n q power n. Yes. And this is also a constant with respect to summation. So, p square q power n, how many times? N plus 1 times, because this is from r is equal to 0 to n. There are n plus 1 terms. So, this is the value of probability of x plus y is equal to n, and substitute this value in the earlier formula. We have probability of x is equal to k given x plus y is equal to n. We started from there, and this is equal to, we have established that x is equal to k into probability of y is equal to n minus k divided by probability of x plus y is equal to n. Substitute all the quantities. This is equal to q power k into p, and this is q power n minus k into p divided by this value we obtained, p square q power n into n plus 1. So, that is the conditional probability is x given x plus y is equal to n is obtained like this. You look, the numerator and denominator, all the factors is q power k, q power n minus k, that is cancel with the q power n, p and p cancel, p square cancel. So, remaining factor is 1 divided by n plus 1. So, what is this? Probability of x is equal to k given x plus y is equal to n, where k have the values starting from 0, 1, 2, etc. up to n alone, because the maximum value of x plus y is equal to n. So, this k can be admissible only the values up to n starting from 0. How many values are there? N plus 1 values. So, 1 divided by n plus 1. So, this is a situation of discrete uniform random variable. So, we have established that if x and y are two independent Poisson random variables with the same parameter p, then probability of x is equal to k given x plus y is equal to n, that is the conditional distribution of x given x plus y, is nothing but it is a discrete uniform random variable. So, such properties we can establish regarding the geometric random variable, and we will discuss more properties of the geometric random variable in the next session. So, thank you for hearing this session. Thank you to all.